Hi, my name is Lauren Fischer, and I'm a junior physics major and computer science minor.
And my name is Andrea Brachmonde. I am a senior physics major, dance minor. And we are part of the gamma ray experimental group at Gonzaga and are presenting our work on a gamma ray detector simulation using GANT4. In figure 1, what was noticed on the NNDC chart of nuclides displaying isotopes ranging in number of neutrons was that the isotopes that are on the outskirts of the image, colored in gray, have little to no information on their energy levels. This, in combination with the isotopes' important applications, is what sparked our interest in researching rare isotopes and isomers and their corresponding energy levels. By measuring gamma ray energies from various beam particles incident on a stationary target, we were able to accurately recreate experimental data, which then validated the results of our simulation. Coded by the students in our group, our simulation was created to utilize a Monte Carlo method in GANT4 to measure the energy of a gamma ray produced in various beam and target combinations. As seen in figure 3, when a beam particle collides with a target nucleus, the beam nucleus becomes excited. Once it is in an excited state, it is unstable and will then de-excite and in turn emit a photon. This photon, called a gamma ray, then enters one of our detectors in our coded detector ring.
As seen in figure 4 on our poster, our simulation uses a sodium iodide scintillation detector. Once the particle enters the detector, the gamma ray is absorbed by material and converted to light, then measured by photomultipliers. Because of the slow nature of the simulation, it was best practice for us to handle data analysis post-simulation so that we could run different analyses after a single run. We accomplished this by recoding the majority of the calculations from being in GANT to root. We are then able to easily gate and view relevant data. One of the many benefits of a computational simulation is the ability to run many different detector target geometries and see which setup produced the greatest yield in gamma ray data. As seen in figure 5, to increase the efficiency of our simulation, we also found it necessary to write code specifically to optimize the detector's geometry for gamma ray detection. For example, for a given displacement between the target and detector ring, it is important that the detectors angle in toward the target, so we coded it to adjust to these findings.
In figure 8 on the left is our data, which showed the emission spectra of cobalt-60 decaying from rest. Cobalt-60 is a common nuclide used as a benchmark in detector calibration. As seen here, our graph produced 2 sharp peaks in addition to the Compton edge and backscattering peaks, which are also identifiable in the Dresden Technical University experimental data. This matching data gave us confidence that both our radioactive processes and measurement of gamma rays were being accurately simulated.
One of our main goals of the summer was to acquire the functionality to shoot a radioactive beam particle. As you can see in figure 6, the right image shows data from the second excited state of carbon incident on a plastic target, and the left, protons on a carbon-12 target. As you can see, both graphs contain 2 peaks corresponding at around 4.4 and 3.3 MeV. These peaks are very good approximations of carbon's 2 lowest energy transitions and thus attest to the validity of our simulation.
Future work includes doing additional realistic simulations of specific reactions that are currently being carried out in labs, and then simulating those reactions that we would like to measure with the eventual detector we built.
Because of the great support we have received on this project, we would like to thank the Gonzaga Science Research Program, Dr. Jim Brown at Wabash College, Jack Winkelbauer at Los Alamos National Laboratory, and our advisor for the project, Dr. Adam Fritsch at Gonzaga University. Thank you so much.